Okay, so this is 6.1.3, and we are going to be connecting ideas about special right triangles and trigonometry. All right, so take a moment and read that essential question to yourself, and go ahead and jot down any thoughts you have about any part of that question. Does anything on there look familiar? Not really sure. Okay. Okay, so here we go. It's okay to not know. Let's go ahead and start. All right. Okay. Oh, whoa, what happened? How did we just pop so far ahead? That was really weird. Okay, here we go. So we're gonna start by reviewing about trigonometry and the special right triangles 30, 60, 90, and 45, 45, 90 triangles. So we're going to first need to fill in we're gonna need to like complete these triangles, solve these triangles, and fill in all of the angles and sides that are missing. So I'm going to go ahead and get my annotation tools going here. So let's see. We have a 30-degree angle, a 90-degree angle. That means that because they add up to 180, this has to be 60 right here. So there's our 30, 60, 90. And then remember that a 30, 60, 90 can be reflected. So like in this case, reflected down to create an equilateral triangle. And if the short side is 1, which is half of one side of the equilateral triangle, that means the hypotenuse up here is going to be a length of 2, twice as big as the shortest side. And then the missing side here, the longer leg, we figured this out in Pythagorean theorem, but we also have a rule for it now that says that we take the short side, so in this case a 1, and multiply by the square root of 3. So this side would be the square root of 3. So I'm going to go ahead and draw that because we don't have a square root symbol. So here we go. All right. 1 times the square root of 3 is just the square root of 3. And then for the second triangle, we have a 45-degree angle, a 90-degree angle, and since they have to add up to 180, that means that our missing angle is also 45 degrees. And then because this is isosceles and has 2 sides equal to each other, this FD is length of 1, ED will be the same length of 1. And then again, Pythagorean theorem gave us the third side, but we also generated a rule for all similar triangles that have 45, 45, and 90-degree angles. And that would make our hypotenuse the length 1 times the square root of 2, or the length of the short side times the square root of 2. Oh, thank you for that. I'm not sure if I can do it with my annotation tools. And I don't know, maybe. I'll try that out. Okay, thank you. Okay, so now I have my 3 sides of my triangles. I'm going to go ahead and talk through a little bit about trigonometry so that we can find the sine, cosine, and tangent of all these different angle measurements. So remember that we have hold on just a second. So remember that we have this this thing that helps us to remember the trig ratios, which are sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So katoa. All right, so we have the SOHCAHTOA that helps us remember which sides to compare for each ratio. So let's start with A, B, and C, where we're finding the sine, cosine, and tangent of 30-degree angle. So that means that 30-degree angle means that we're establishing our reference angle as the 30-degree angle. So I'm going to locate my 30-degree angle right here. And in order to find the sine, cosine, and tangent of 30 degrees, I need to identify the opposite, adjacent, and hypotenuse of my triangle in relation to that angle. So remember, in any right triangle, the longest side opposite the right angle is always the hypotenuse. And then the other side that forms the angle that we are focusing on here, that forms 30 degrees, would be the adjacent side. So the hypotenuse in this triangle is 2, the adjacent side in this triangle is √3, and that leaves the opposite side over here to be 1. All right, so now that we've labeled those, we have all the information we need to set up our sine of 30, cosine of 30, and tangent of 30. So remember, the sine of 30 is going to be, we're using the SOH part of SOHCAHTOA to remind us that the sine, S, is opposite over hypotenuse. So that means 1, which is opposite, over 2, which is hypotenuse. So the sine of 30 is 1 over 2. So then let's do the same idea with cosine. Now, CAH tells us the cosine of the 30-degree angle is the adjacent side over the hypotenuse, that ratio. So adjacent is √3, hypotenuse is 2. So the cosine of 30 is √3 over 2. And then TOA, T-O-A, helps us to remember what the tangent ratio is. So the tangent of our angle will be the opposite O over the adjacent A. So the opposite of 30 degrees is 1 over the adjacent, which is √3. So the tangent of 30 is 1 over the square root of 3. Okay. Now, these are exact answers because we didn't use any decimal approximate values. So √3 over 2 is irrational. And when we actually put this in as a decimal, we would get something we'd have to round off. So if you punch in sine 30 in your calculator, you should get 0.5. If you punch in cosine 30, you would get the decimal approximation of this fraction. And same with tangent 30, you get a decimal approximation of this fraction. But we do need to know how to find these exact values. And in fact, these numbers become so important in trigonometry when you get into more advanced topics next year and beyond that, that you'll get to a point where you'll have these fractions memorized because you use them so much. It's sort of interesting. But right now, we're just getting an intro to it. So now we need to do sine, cosine, and tangent of 60 degrees. So what that means is I need to switch which angle I care about in this 30, 60, 90 triangle. So I'm going to go ahead and change my color so that you can see the difference here. And I'm going to circle the 60-degree angle. So this time I'm using a little light green color. And this is actually going to change my opposite and adjacent sides. The hypotenuse will stay the same. So there's the hypotenuse. But opposite and adjacent are going to switch because now my reference angle is up here. It's formed by the hypotenuse and the side adjacent to it. So I need to, in green, identify that this is now the green angle's adjacent. And this is now the green angle's opposite. So when you switch your angle of reference, you also switch the opposite and adjacent. So for now, I am actually going to ignore these pink opposite and adjacent. All right, so now in relation to the 60-degree angle, Sine is opposite over hypotenuse. So in this case, it's root 3 over 2. So let's go ahead and draw that in. Root 3 over 2. And then the cosine is adjacent over hypotenuse. So that's 1 over 2. And then the tangent, opposite over adjacent, that's root 3 over 1. Notice the relationship between the sines and the cosines. Do you see how their numbers are the same, but they just switched? It's because we switched angles, we switched values. It's interesting that way. But there's a lot of patterns that you can keep an eye out for. All right, now our last 3, we have to use the other triangle. So we get to just shift gears over here and use the 45-45 triangle. All right, so we're gonna need to label our opposite, adjacent, and hypotenuse for the 45-45 90. So if we are taking the sine of a 45-degree angle, it doesn't matter which 45. So I'm just gonna circle this one and use that for the rest of it. But I could have used this one. You'll get the same numbers. Either one is fine. Since we have an isosceles triangle, we get a little flexibility there. So now I'm gonna label my hypotenuse up here. And my adjacent down here. And then that leaves this one to be my opposite. Okay, my font is pretty big, so it's spilling over the edge there. All right, good enough. Okay, so now I have my triangle labeled here. I'm just going to set up my ratios for sine, cosine, and tangent on the third triangle. And I think a lot of people have already done this. You're working ahead because you're seeing the pattern, you're feeling like confident. That's awesome to see. But that's fine if you're not. Also, you just follow along with me. So go ahead and sine of 45 is opposite. Remember, go back to SOHCAHTOA. Sine is opposite over hypotenuse. So 1 opposite over root 2. Okay. And then cosine of 45 is adjacent over hypotenuse. So again, we have 1 over root 2. And those two values are equal to each other because we're in an isosceles triangle. So it doesn't matter which angle we use, and those two ratios are interchangeable. And then the tangent of 45 is the opposite over adjacent. So in this case, that's 1 over 1. And it wouldn't matter which way we had that either. It would always equal to 1. And again, if you punch in your calculator sine 45, you'd get a decimal equivalent to this. If you punched in tan 45, you'd get 1 every single time. Even for a bigger triangle, that would still hold. Remember, these are isosceles. So if this was 8 and 8, 8 over 8 would reduce to 1. We have the same ratio no matter how big or small the triangle is. Okay, so here we go. So now in these fractions, we're not quite done with how we want them to be going forward. A few of them are not in exactly the form we want. So when we're dealing with fractions that have radicals in them, like square roots, it's really important that the denominator not have a radical. So you can see in part C, we have 1 over root 3. We need to figure out how to deal with this 1 over root 3 to get the root 3 out of the denominator. We can also see that down here, this and this have a root in the denominator. So we're going to go ahead and learn how to do something called rationalize the denominator, which will help us to rewrite those 3 fractions without a root in the denominator. Okay. So here we go. All right, so this is just like a side mini lesson on how to rationalize the denominator of a fraction. So we have a square root down here, 1 over the square root of 5. Here in example 2, 7 over the square root of 7. And here we have 2 over 3 times the square root of 3. Each one has a square root in the denominator. So we just need to know what it looks like for how to simplify each one of these so that there is no root in the denominator anymore. So a quick side note, something to keep in mind is that when we square a square root, like say I take the square root of, I don't know, 3, and then I square it, I end up getting the number itself. Square roots and squares are inverse operations. So when we multiply a square root term by itself, essentially the square root symbol is gone. It undoes the square root symbol. So in order to get that root out from the denominator, like to get rid of root 5 from the denominator, what I want to do is multiply it by itself. So what I'm going to do is I am going to multiply this by the square root of 5 over the square root of 5. And the reason I'm allowed to do that, and it doesn't mess up my fraction in terms of its value, is because anything over itself is 1. So root 5 over root 5, that's just a 1. But I'm going to change the way that the fraction looks because of this. So that root 5 times root 5 down here is essentially root 5 squared. And then on the top, I have 1 times root 5, which is just root 5. So now I have one last thing I need to do to simplify. And that would be to simplify the denominator. So when I square the square root, I just get a 5. So on the top, I still have this square root of 5. But on the bottom, I just have a plain old 5, which is rational. And that's what we were going for. So that was the goal. So there's our rationalized denominator. Okay. So we're going to do the same thing for example 2 and example 3 and see what happens when we have like a different number kind of up in the mix besides a 1 on top. So for number 2, instead of using root 5 over root 5, we use root 7 over root 7. So I'm going to go ahead and multiply this now by the square root of 7 over the square root of 7. Okay. All right. Okay. All right. So now we're going to multiply across the top and the bottom. So on the top, we have 7 times the square root of 7. And on the bottom, we have the square root of 7 squared. And remember, when we square a square root, we get just the number underneath. So now we have 7 root 7 over 7. And actually, we're not quite done. So I have one more step I can do. Because the numerator had a 7 in it, these 7s are going to cancel. And our final answer will be just a root 7 in this problem, or root 7 over 1. So sometimes that happens. So I'll put a box around my answer here. Okay, and then we're going to do this last one, and then you can practice. And if you feel like you've got it and you want to work ahead and work on 1, 2, or 3, knock yourself out. Okay, so now I'm going to go ahead and do this one more time. So in this one now, I want to get rid of the root 3, so I'm going to multiply by the square root of 3 over the square root of 3. And that will get me 2 root 3 on the top, and 3 times the square root of 3 squared on the bottom. Sorry, it's a little squishy there. And so then that gives me 2 root 3 on the top over 3 times, and this right here, this part right here is another 3. So finally, we'll have 2 root 3 over 9. And it doesn't look that pretty, but it is rationalized. Our denominator does not have a radical in it. So I'm gonna go ahead and box my answer. All right, so it's your chance to practice these last three a little bit. Okay, we're gonna check our answers. So on number one, you should have multiplied by root 2 over root 2, and the answer is, oops, I'm still in highlight mode, sorry. The answer is root 2 over 2. For number 2, that's fine, glad you're back. For number 2, we multiply by root 3 over root 3, and we end up with 3 root 3 over 3, which is just root 3. And then finally, we multiply number 3 by root 7 over root 7, and that would give us a final expression of 5 root 7 over 2 times 7, which is 14. All right, so double check your work on that for those of you who did them. Okay. All right. All right, so I'm going to go ahead and clear this. Hopefully you got your examples at least. Okay. And now we're going to go back to that list of problems that we did from the previous slide. So here, do you see how the 3 I circled need a rationalized denominator? So we go ahead and rationalize the denominator for each of these. It's really just 2 little problems because sine 45 and cosine 45 are the same. All right, so if we wrote this in rationalized denominator form, you should get that 1 over root 3 can be written as root 3 over 3. And that 1 over root 2 can be written as root 2 over 2. So that would make this a root 2 over 2 as well. Okay, clearing, here we go. All right, so now what we're gonna do is start connecting these like trig functions like sine and cosine. We're gonna connect them to a right triangle. So our first part, it's going to seem like 2 separate problems until the end when we find out this whole thing. So use the Pythagorean theorem with the given triangle to complete this equation. So remember, Pythagorean theorem is a squared plus b squared equals c squared. But if we don't have a, b, and c, we can use whatever numbers or variables that are given to us. It's our leg squared plus leg squared equals hypotenuse squared. So in this triangle, it's x squared plus y squared equals 1 squared. That's right. I see several people have done that already, so I'm going to go ahead and put those in there. So this is an x, and this is a y, and this is a 1. All right, so this triangle is just sort of a general triangle. Remember, the ratio of the sides to each other is, as long as we know what the angle is going to be similar to every triangle with the same angle. So if I choose the hypotenuse to be a length of 1, it doesn't really matter because in the end it would reduce to the same thing as this would. So we get to pick, which is kind of like if it's more generalized like this, we can pick the hypotenuse to be a 1. And then these can be changing depending on how big of an angle we're looking at. So now we're going to do what is the sine and what is the cosine from this triangle. And in order to do that, remember, we need to always label our sides. So in relation to theta, we have our hypotenuse. We have our adjacent down here. And that makes this side our opposite. And then when we think about SOHCAHTOA, remember SOHCAHTOA, so I'm maybe I'll type that in here for just reference. Sine is opposite over hypotenuse. So in this situation, opposite is y, hypotenuse is 1, so it's y over 1. And since we don't need to write the 1 over 1, we can just write y. So the sine of theta in this triangle is y. And the cosine of theta in this triangle is the adjacent over hypotenuse, x over 1. So more simply, that's just x. All right, so now what we're going to do is we're going to sort of combine these two things together to come up with a pretty cool little rule. So in part C, it says to use substitution and complete the equation. So let's look for the substitution that's happened here. Sine theta squared plus cosine theta squared. So it looks like what they're using is Pythagorean theorem. We have an x squared and a y squared here. It looks like sine was substituted in for y, and cosine was substituted in for x. And remember, when you're adding things, it doesn't matter which one comes first. So you can write it sine squared plus cosine squared or cosine squared plus sine squared. It doesn't really matter. So when those things were substituted in, this is the expression that happened. And the only thing left is what's over here. Well, we didn't actually mess with this. So what is 1 squared? 1 squared is 1. So this thing right here, sine theta squared plus cosine theta squared, is actually a very special rule in trigonometry. So we knew the Pythagorean theorem. We knew how to find sine and cosine. We just, because sine theta is equal to y, we plug it in for y here. Because cosine theta is equal to x, we plug it in for x here. And that gives us an equation of like cosine squared plus sine squared equals 1 squared. And in this case, that means it's equal to 1. Okay. All right, so this is sort of a general summary of the Pythagorean identity. Okay. Okay, so an identity in math is an equation that is true for all possible values. A trig identity is an equation that involves trig functions. It's true for every single value. And then the most common trig identities are those involving Pythagorean theorem. So this is basically like a formula. And it's always true, no matter what your theta is. So if you had an angle of 1 degree, it would be true. If you had an angle of 30 degrees, it would be true. It doesn't matter what your angle is, it's true. It's a true equation. It's like the Pythagorean theorem, but for trig. Okay. All right. Now we are going to veer back to that and see how to use it in a minute, but we're going to do a different type of problem right now to find missing side lengths using trig and Pythagorean triples, and then we'll circle back to the Pythagorean identity. Okay, so now in this problem, it says use what you know about right triangles, Pythagorean triples, and trigonometry to answer the following question. Angle theta is an acute angle in a right triangle. If cosine theta is 9 over 41, what is the sine of theta? So one way to do this would be to take this expression 9 over 41 and put it into that formula we just learned about, and then work backwards to solve for sine. And you could do that. Another way is to draw a generic random right triangle with a theta in there, and then put the information from this first equation into the triangle. So here's what we're going to do. So I'm showing you two methods today. So first, we're going to label our triangle. Theta is right here. That makes this the hypotenuse. That makes this the adjacent. And then this is opposite. Okay. And now remember in SOHCAHTOA that the cosine is adjacent over hypotenuse. So what that tells me is that, actually, let me change my color, is that this 9 is the adjacent side, and this 41 is the hypotenuse. So I can go back to my triangle, and I can put those lengths on those sides. 9 is adjacent, so I'm going to just type a 9 right here. 41 is hypotenuse. And once I have that, the next thing I need to figure out is what third side, because if I know the third side, I can find the sine. Because I know that the sine of theta is equal to the opposite side over the hypotenuse. So in order to complete this and actually get that fraction, I need to know the opposite side. And look, this thing is a Pythagorean triple. So let me go down to my triples. 9 something 41. Oh, look at that. There's the one we're looking at, 940, 41. So that tells me that the third side that we didn't know is 40. And now I can complete my equation. So now I can write my equation as the sine of our angle, theta, is 40 over 41. Okay, so we're going to do this again. Oops, I went too far. Okay, so now for part B, angle theta is an acute angle in a right triangle. If the sine of theta is 8 over 10, what is the cosine? So now remember, this is actually something we can adjust from the beginning. Remember that the sines, cosines, and tangents are all equivalent to each other. So it doesn't matter if we have, our fractions 8 over 10 or if we reduce it. So I'm going to reduce this fraction first because it's going to make my life a lot easier to find my Pythagorean triple. So what I'm going to do is, before I even start, I'm going to reduce my fraction. So sine of theta is 8 over 10. I'm going to rewrite it as the sine of theta is 4 over 5. Because I don't really care about the actual lengths, I just care about their ratios, because all I'm trying to find is the cosine of the theta. I don't care about necessarily finding the precise length of the side. So now I'm going to go over to my triangle, and I'm going to label my sides opposite, adjacent, and hypotenuse. So here's my hypotenuse, adjacent, opposite. And then I'm going to sub in the values from the sine that I just did. So like this, oops. So sine is always the opposite over the hypotenuse. So let's go. Opposite is going to be 4. Adjacent is going to be 5. And that means my third side, which is what I'm trying to find. This happens to be a 3, 4, 5 triangle. 3, 4, 5. So our missing side is a 3. So let's type that in. There's a 3. And now that we know it's 3, 4, 5, we can find the cosine. So the cosine will now be adjacent over hypotenuse, which is 3 over 5. So the cosine of our angle is 3 over 5. If we hadn't reduced, we could still do this. We would find that the cosine would be 6 over 10, which is just the double. But again, it reduces to the same thing. So it doesn't matter if you have it in reduced form or not. So if you see the original fraction they give you is something that could be reduced, go ahead and do it. All right, so here's our last slide where we're gonna do that Pythagorean triples method again, and then we're gonna solve the same problem using the Pythagorean identity, and we're gonna see how it's two methods for the same exact end result. So here's our question. Angle theta is an acute angle in a right triangle. If cosine of theta is 5 over 13, what is sine of theta? So I want everyone to take a moment and do this Pythagorean triple style. Do this in the box on the left, the way that we were just learning, and then we'll go through the second method, Pythagorean identity, altogether in more careful detail, okay? All right, so I'm going to go through this pretty quickly and you can check your work. Okay, so again, we need to start by labeling our triangle. So that's hypotenuse, adjacent, opposite. And then I have my numbers for my cosine equation up above. So here's my cosine equation from above. So we have cosine is 5 over 13. And remember, cosine is always adjacent over hypotenuse. So this is a 5, this is a 13. And then you can see the missing side. You can get it from finding the Pythagorean triple, and it looks like this is a 5, 12, 13 Pythagorean triple. So I'm back to my triangle. That would mean that the third side had to be a 12. So now I can write my sine expression or sine equation. Sine of theta is opposite. So we're trying to find sine. So sine of theta is opposite over hypotenuse. In this case, that's 12 over 13. Yay. All right. So that's one way to find that. Be careful with your ratios that the opposite is always the top of the fraction and the hypotenuse is always the denominator. It's really, really important. Otherwise, it's be off. It's 12 on the top over 13. Okay, now I'm going to go ahead and show you how we get 12 over 13 with using the Pythagorean identity as well. So what we're going to do is we are going to plug in what we know about the cosine being 5 over 13, and then we're going to solve for the sine. Okay, so I am going to get my writing tool here. All right, and I'll try to make this as neat as I can. So what I have is sine of theta squared plus, and now cosine is 5 over 13, so I'm going to plug that in. 5 over 13 squared equal to 1. So all I did was substitute the value for cosine. And then I'm going to square my fraction. So I still have here a sine of theta squared plus square the top, square the bottom. That's 25 over 169 is equal to 1. And now I'm trying to isolate my sign because remember, I'm trying to solve for sine. So I need to subtract that fraction on both sides. All right, so I'm going to subtract 25 over 169 on both sides of my equation. And what that's going to leave me here is I have sine of theta squared equal to, and now here is a little tricky thing. So I need to do this. I need 1 minus 25 over 169. So I'm going to do a little side fraction subtraction problem. So in order to do 1 minus 25 over 169, I need a common denominator. So what I can do is rewrite the 1 as 169 over 169. There's our 1 minus 25 over 169. And when I subtract those, I get 144 over 169. So that's what I'm going to go ahead and put over here. 144 over 169. Okay, and now I have my very last step, and then we have our answer. So I want to find sine theta, not sine theta squared. So I'm going to square root both sides of my equation. And that will give me that the sine of theta, oh, I can't get that to be nice. The sine of theta is equal to, and we square root the top and we square root the bottom. So the square root of 144 is 12, and the square root of 169 is 13. And look at that, we got the same exact answer, sort of more algebraic style. Okay. All right, so if you're really, really uncomfortable with adding and subtracting fractions, I could totally understand that this could be stressful for you, but some people really like this because it works every time, and it doesn't take a bunch of extra drawing pictures and locating your Pythagorean triples list or your special triangles list. Like, it works no matter what, this equation. So there it is.